Okay, welcome back, calculus. We are continuing with our 4.5, which is our U-substitution for integrals, and we're on example number 5. The other videos showed examples 1, 2, 3, and 4. So we want to integrate cosine 4x times the sine of 4x with respect to x. And I know you're probably thinking, oh, well, in the last couple of examples, you put what was in parentheses as your u. Well, this time what's in parentheses is 4x here. And if I do that, there's no way I'm going to get rid of my sine and cosine at the same time. I don't know what function has a derivative of cosine u sine u. So we want to let one of these trig functions actually become our u, because the derivative of sine of any angle is the cosine of that angle times the derivative of the angle. And when you take the derivative of cosine, you get negative sine. So I can go either way with this. I think to stay away from negatives, I'm going to come over to the side here, and I'm going to say let u equal the sine of 4x. du, therefore, I don't need a negative sign here now because the derivative of sine is cosine of the same angle, and then chase it with the derivative of that angle, right, like that, and then dx. So this gives me, I'm just going to make it nice and neat. I'm going to pull the 4 to the front. 4 cosine of 4x dx. So this right here would end up being my u. And then all of this, all of that, would end up being, well, we got to figure it out, because right here I have cosine 4x dx, and over there I have 4 cosine 4x dx. I don't need this 4. Let's get rid of that 4. And then I'll just have cosine of 4x dx, which tells me that what I circled over and up here is now going to be replaced with just plain old 1/4 du. So this is 1/4 du. And now everything's been circled. Everything is now gone from being in terms of x's to being in terms of u's. This becomes the integral of u times 1/4 du. And the 1/4 can come to the outside, and it's just the integral of u with respect to u. Kind of weird, but maybe it'll click better when we do our check. We'll see what happens here. When we integrate u with respect to u, we just get u squared over 2. Of course, we copy our constant multiple of 1/4 and add our constant of integration. This gives me 1/8 u squared plus c. I got to bring my u back in terms of x, so it's 1/8 sine of 4x quantity squared. So I can put big parentheses in square, or I can put my square right there, which I prefer to do, plus c. This turns out to be the original antiderivative function I'm looking for. Okay? Let's check this. I'm going to go ahead and write check. And we simply take the derivative with respect to x of the answer that we had. 1/8 sine squared of 4x plus c. Now, if you'd like to rewrite this to put it in your more of an exponent form in order to see your power rule happen, you can, although I don't think it's necessary. I'm going to take the 1/8, multiply it by this 2, and get 2/8 sine to the first of 4x. Now, what is the derivative of sine of 4x? That's cosine of 4x. Now times the derivative of 4, which is 4x, which is just plain old 4. So 2 over 8, is 1/4. Multiplied by this 4 makes all those numbers go away. And you just end up with sine of 4x, cosine of 4x, and I know I didn't say it, but plus 0. So I end up with the same thing I started with. So what if it's backwards? It's still logically equivalent because multiplication is commutative. So this does indeed check, and I'm good to go. I could have done a u substitution allowing the cosine of 4x to be my u, and then when I took the derivative of cosine, I would have ended up with a negative sine of 4x times 4 dx. But then I would have had to divide it by the negative, and I would have been introducing a negative for no reason whatsoever. I don't need to bring in a negative, but we're done with the problem, and I do end up with 1/8 sine squared 4x plus c. If I had done the other substitution though, I would have ended up with something with a cosine squared in my answer. But I can always switch from sine squared to cosine squared using that basic fundamental Pythagorean identity. That sine squared x plus cosine squared x equals 1, or sine squared theta plus cosine squared theta is equal to 1. All right, this wraps up question number 5, and I will move on to question number 6. Okay. And question 6 is asking me to integrate 10x squared over the square root of 1 plus x cubed with respect to x. So, what do we see? This is a nice plus sign right there. I'm hoping that you recognize that whatever's under this square root sign, the square root sign is serving as a set of parentheses to a 1/2 power. So this oogie boogie might be what you want to go for. If you take this derivative, you end up getting 3x squared. I have a 10x squared, so you can see you're off by a constant multiple. Instead of a 3x squared, I need a 10x squared, and I can make that happen because I can divide by that 3 and input that 10, and we'll make it work out. So I'm going to come over here to the side, and I'm going to say let u equal 1 plus x cubed. Now I don't want the square root of 1 plus x cubed because I certainly don't want to take the derivative of the square root function, but I do want whatever's inside of my square root. My du is therefore 3x squared dx. I don't want a 3x squared, I want a 10x squared. So I am going to get rid of my 3, and I am going to put my 10 in. So I will multiply by 10 here to input that 10 onto my x squared, but I must mimic that over on the left-hand side of the equation in order to balance. All right, 10x squared dx. All of this right here becomes 10/3 du. And this down in here is my u. The square root symbol is fine. Everything is going in terms of u. Everything seems to be circled. This is now the integral of, and I'm just going to put 10/3 du on my numerator, even though I'm going to clean this up in just a minute, over the square root of u. So, I'm going to turn this into 10/3 u to the negative 1/2 du. Negative 1/2 because, of course, the square root symbol is on your denominator, but I would like to use it as a power rule, so I'm going to bring that up to the numerator and put a negative symbol on my exponent. 10/3 is coming outside, u to the negative 1/2 du. So I'm going to copy my 10/3. This is u to the, what do I get when I add 1 to a negative 1/2? I get a positive 1/2 divided by a positive 1/2 plus c. Alrighty? Okay? So when I take 10/3, I'm just going to take baby steps here. If you divide by a half, that's the same thing as multiplying by 2 over 1. And u to the 1/2 is like the square root of u plus c. So this is going to give me 20 over 3 times the square root of, and my u was 1 plus x cubed plus c, and I do believe that is going to be the antiderivative function for this integrand right here, or it's the integral of my original question. Okay, so let's check this. And I'm going to take the derivative with respect to x of the thing I just boxed. 20 over 3 times the square root of 1 plus x cubed plus c. So I'm going to rewrite this so I can use my power rule. This is 20 over 3, 1 plus x cubed, quantity to the 1/2 plus c. And we're going to take the derivative of this. The 1/2 will come down and multiply by 20 over 3, giving me 10 over 3. Or if you will, I can keep the 1/2 there for a minute and leave the 20 over 3, and then you'll see that's just 10 over 3, a lot easier. 1 plus x cubed. I need to now subtract 1 from my exponent to take a derivative. Derivative always knocks the exponent down by 1. 1/2 minus 1 is a negative 1/2. chase this sucker with the chain rule of my oogie boogie, which is 3x squared. And then plus 0, because the derivative of any constant is 0. This is going to give me 10 over 3. The 3x squared is going to stay on my numerator, 3x squared. And this, because of the negative exponent, I would like it to go to the denominator as the square root of 1 plus x cubed. And it looks like my 3's are going to divide off, and I'm going to end up with 10x squared over the square root of 1 plus x cubed. This is definitely the original integrand that I had in the question, so I did indeed check my answer, and I'm good to go. And that is the end of question number 6. You now have 6 examples. Let's not forget what to do. We need to find a u, which is a function of x, such that the derivative of u is sitting in the integrand as well. And it might be exact or it might be off by a constant multiple. And then you're going to go through your du business. You're going to solve for the extra stuff that's in your integrand, including your dx. And you're going to substitute this du piece for everything else that's sitting in there. Do your substitutions, bring everything back in terms of u, simplify it down, make it nice and neat before you integrate, and then simplify your integration, box your answer after you put your x's back in. Don't forget, this original question was all x's. They expect you to have all x's in your answer, no u's. Do your check by taking the derivative of what you believe the answer is, and it better bring you right back to what the original integrand was for your integral question. Okay? All right, talent out.